will share my screen. Okay, I will share my screen. Okay. Okay, can you see my screen? Can you hear my voice? Can I get your response? Boleh nampak screen saya? Boleh dengar
Yes,
suara? Is my voice clear? You can hear my voice clearly or not?
Yes, Doctor.
Okay. Thank you for the response. So, last week we have learned up to this slide. We have learned up to this slide. Okay. Okay, we have learned up to this slide. So this is about the AM modulator block diagram. Okay, so last week I already explained to you about this process. Okay, so this is the process inside the transmitter. Okay, so if you remember the transmitter, okay, so before we can transmit the signal into the medium, we need to do the modulation process to convert the input message into an electromagnetic wave or radio wave which is suitable for transmission into the wireless medium. Okay, so this is the block diagram for the AM modulator circuit, SSB, single sideband modulator, which will generate the single sideband without carrier. Okay, and I already explained to you about the equations involved in the process of generating the signal. Okay, and for your information, as I told you previously also, that this slide has been asked in the previous final exam question. Okay, pernah ditanya dalam exam yang lepas. Okay, we have asked this question a few times. We use the same kind of block diagram, only we change a little bit about the equation for the input message. Okay, and if you remember last week I have explained about this, that we can find the equations. So for example, if you are given equations VMT over here, okay, and you are given a VCT over here for the carrier, and you need to know how to find the equations for the output of each balance modulator. So we have balance modulator 1, balance modulator 2, and remember that balance modulator will do the process of multiplication in time domain. Okay, and you need to know what is the equations in point A, point B, point C, and point D, as I already explained last week. Okay, so phase shifter will change the input message or the carrier. We have two. So if the equation is sine wave, if it is a 90-degree delay, it's gonna be cosine. Okay, similar for cosine function. If it is 90-degree delay, it will be sine function. Okay, so sine become cos, similar cos, cosine, so cos will become sine. Okay, after it goes through the 90-degree phase shifter. Okay, and for the A at point A, it is VMT multiplied with VCT. Okay, similar at point B VMT multiplied with VCT. Okay, so balance modulator, again I explained, it will do the process of multiplication in time domain. Okay, so when you multiply both function, you're gonna get upper sideband and also the lower sideband, and then it goes through the adder. Okay, goes through the adder will add A and B. So after it add A and B, okay, you're going to see that the output at point C would be a single sideband without the carrier. And from my previous explanation, you're going to get a lower sideband for this example, okay? And then here we have amplifier with gain of A, okay? So you need to multiply the amplitude of the signal. So that means at point D it is equal to point C multiplied with the gain. Okay, so you will amplify the gain and you will get the output as a single sideband. From here you can draw the frequency spectrum. Okay, you can draw the frequency spectrum and you can find the bandwidth. The bandwidth is equal to Hm, and you can find the P total, which is in this example is PLSB. Okay, so this is VLSB, so you can get VLSB square divide with 2R, so you will get the answer in terms of watt. Okay, so in the previous exam we have asked until power calculation. For this kind of question, we have asked until power calculation. Okay, so you can learn again from the previous from the recorded lecture video in the YouTube, so that you can have better understanding about this. Okay, so the question is not difficult actually, because it only involves multiplication of trigonometry and then draw the spectrum and then find the total power. That's it. Okay, it does not involve complex analysis to find the answers. Okay, and this already explained, you can read on your own. Okay, so up to this slide, okay, up to this slide, so this is about transmitter system, a modulator in the modulator circuit inside the transmitter system. Okay, and starting from this slide, it is about the demodulator, which is a part of the receiver. Okay, so where are we now? We are learning about a receiver part. Okay, so we have seen previously the modulator, which is in the transmitter. Now we want to see the receiver. Okay, so for example, this is the receiver. Okay, the receiver. And demodulator, you're going to see that demodulator is the last process happens inside the receiver. Okay, so demodulator circuit is somewhere here. Okay, and there are many other processes involved inside the receiver before we can do the demodulation process. Okay, so so your notes, your lecture notes, okay, in your lecture notes, it begins by explaining about the demodulator. Okay, we haven't seen yet what happened at the front end of the receiver. Okay, so I just want to tell you that your lecture notes, okay, begins explaining about the receiver part by explaining about the demodulation process. And demodulation process is the back end process inside the receiver. Okay, you're going to see later what happened before the demodulation. There are a few processes involved. Okay, so about demodulator, okay, there are two types of demodulator. So this is also similar with the modulator circuit, where we have two types of modulator. Okay, and for this one, for the demodulator, we have a diode detector and also transistor detector. Okay, and this is the general circuit for the diode demodulator. Again, you do not need to memorize the circuit. You do not need to memorize the circuit. Okay, because circuit can be any circuit. Okay, what you should understand is up to the block diagram. Okay, we are not asking about the circuit because circuit will be asked in different subject. Okay, so if you see from this demodulator circuit, so the input here is AM signal, which is double sideband full carrier signal. Okay, so there's a coil over here, and here is a capacitor which only allows the AC current, and then here we have the diode which only allows current to flow in one direction only and prevent reverse bias. Okay, so this diode is like a switch, okay, which will switch on and switch off. Okay, so if you see that current can only flow in one directions and prevent reverse bias, so that means during the forward bias you're going to see that the current will flow to these directions and it will charge the RC tank circuit. So this RC tank circuit is like a LC tank circuit, which will store and discharge the energy. Okay, it will charge during the forward bias of the diode, and it will discharge during the reverse bias of the diode. Okay, and this capacitor C2 will remove the DC voltage and allows only AC voltage to flow in the circuit. Okay, so C2 will remove the DC voltage. So what happened actually? Okay, so so we're gonna see what is the how does the waveform looks like when it goes through the processes. Okay, so this one. Okay, so I will explain about these waves so that you can have better understanding about what happened actually. So assuming that initially we have the input of double sideband full carrier. Okay, remember double sideband full carrier, how does the waveform looks like? Okay, so there's another, wait, maybe I can draw like this. Okay, so there's another side, there's a negative side over here at the input. So this is what happened initially in the input. So there's a full wave of double sideband full carrier at the beginning from the input. Okay, and there's no this one, there's no this one. Okay, so this is like a okay, so maybe I will erase this one. Okay, wait, I will draw completely. For example, this one is okay. So in ECS, in this subject, in ECS subject, we like to ask student about their understanding about the process happens inside the circuit rather than asking about the circuit. Okay, so initially is double sideband full carrier as usual. Okay, seperti biasa double sideband full carrier. So this is before the diode. So what happened after the diode? Okay, after the diode, okay, diode only allows current to flow in one direction only, so that means the negative cycle will be removed like this. Okay, so this is right after the diode. Okay, so if you see from here, so at point A, so at point A is a full wave. After the diode, at point B, it's only half of the wave. Okay, and then what? At point C, we have at point C and at point D. Okay, point C is right after the RC tank circuit. Okay, what happened after the RC tank circuit? Remember, RC tank circuit will discharge during the reverse bias of the diode. Okay, so what happened? What happened is that, so I gonna erase this one. Okay, so I erase this one. So the output will looks like this. So instead of going down, okay, the wave will gradually move downwards like this. Okay, so RC tank circuit will discharge at this point to make sure that the signal will not drop towards the negative cycle. Okay, so instead it will gradually decrease like this. Okay, and then forward bias again. Okay, forward bias again, and then reverse bias. Forward bias, reverse bias. Okay, forward bias and then reverse bias. So reverse bias, the RC tank circuit will fulfill the voltage when it drops. Okay, when the signal wants to drop towards the negative cycle. So you're gonna get this kind of wave. You're gonna get a sine wave like wave. Okay, a sine like wave like this, but with a sawtooth like this. It is not smooth. Okay, so right after the diode, you're gonna get this kind of wave, the red color here. So this is like a sine wave, but located above a certain voltage. Okay, so this is a DC voltage. So this is a DC voltage. So the output at point C, right after the tank circuit, RC tank circuit, will looks like a sine wave, but above a certain voltage. Okay, so there's no this one there's no wave like this. Okay, only the red color. Okay, so this is right after the RC tank circuit. And then what? And then after the RC tank circuit, there's another capacitor. Remember, capacitor only allows current, alternating current, AC current, and remove the DC voltage. So that means what happened is that the wave will drop into the wave will drop towards the x-axis because the DC voltage has been removed. Okay, so I will redraw the x-axis. Okay, so that it becomes so right after C2, the wave will drop to the x-axis. So I redraw again the x-axis to be here. Okay, saya lukis semula paksi X. I redraw the x-axis. Okay, so at point D, you're gonna see that the wave drops and center at x-axis. Okay, and it looks like a sine wave, but with sawtooth like a sine wave. Okay, it is a sine wave, but not smooth. It has a sawtooth shape like this. Okay, so in order to make it smooth sine wave, we need another filtering process. Okay, to make the wave more smooth like a original shape. Okay, so this is at point D. So you're gonna get sine wave centered at x-axis. Okay, capacitor C2 remove the DC voltage. So do you have question to ask? You can ask question. Okay, so at the end you're gonna get this sine wave is actually the VMT at the output. Okay, so this sine wave is actually the VMT produced by the demodulator at the output. Okay, so if you have question you can ask. So for your information, we haven't asked this question yet. Okay, kita belum pernah tanya soalan seperti ini. Okay, but if we gonna ask this question, we're gonna ask you to sketch the waveform at 4 different points. We want you to know, we want you to understand what is the wave, how does the wave looks like at point A, and then point B, point C, and point D. Okay. And then the next type of demodulator circuit is the transistor detector or transistor demodulator. So the concept is similar with the diode detector. If you see from here, we have a transistor over here and the input is over here. And this input signal is controlled by R2 and R1, okay, and it will go through the base of the transistor. Okay, so if the base of the voltage at the base of the transistor more than the voltage of the threshold, okay, then current can flow from collector to the emitter. Okay, and when current can flow from collector to the emitter, that means it is a forward bias. And during the forward bias, at the same time, R3 and C2 will charging. Okay, and then when the voltage at the base of the transistor drops below the threshold limit, what happens is that current cannot flow towards the emitter. Okay, so if the voltage at the base drops below the threshold voltage, current cannot flow from collector to the emitter. Okay, so what happened? What happened is that this RC tank circuit will discharge. Okay, and this capacitor C3 will remove the DC voltage, and the output here, the output wave will be centered at x-axis. Okay, you're gonna produce a double sideband full carrier at the output. Okay, you're gonna produce double sideband full carrier at the output. Okay. Sorry. Not double sideband full carrier. This is not modulator, sorry. So you're gonna produce, wait. So you're gonna produce at the output of demodulator is a sine wave, which is VMT. VMT. Okay. Of course, the output is not smooth. The output is not smooth, just like in the previous example. Okay, and if you want to make it smooth, we need another filtering process so that the output gonna produce a smooth sine wave of VMT. Okay, so now we want to see how can we demodulate the double sideband suppressed carrier or single sideband. Okay, how to do that? Okay, so if you see from this block diagram, this is for the double sideband suppressed carrier and single sideband demodulation. Previously is the double sideband. Okay, in the previous slides it is about the double sideband full carrier demodulation process. Now we want to see how does the double sideband suppressed carrier and single sideband demodulation process. Okay, from this slide. So if you see from here, all of this is the demodulator block diagram. Okay, although there are balance modulator, you see here balance modulator, but this is inside the demodulator circuit. Okay, so inside the demodulator circuit there are actually a modulation process that helps to do the demodulation process at the receiver. So you see that here we receive a single sideband with carrier. Okay, we receive a upper sideband, okay, of the we receive a upper sideband. Okay, so here in the input you see that here is FC, we receive signal the upper sideband FC plus FM. Okay, and there's no lower sideband, there's no carrier component. Sorry, this is about single sideband without carrier. So this is a single sideband without carrier in the input. Okay, so we receive single sideband without carrier in the input, and we want to produce the original signal frequency, which with the frequency of FM only. So what we need to do is we can use a balance modulator and have the input multiplied with the local oscillator frequency, which tune to the carrier frequency. Okay, remember balance modulator will do the process of multiplication in time domain. So you will multiply both inputs. Okay, and when you multiply, remember when you multiply you will produce upper and lower sideband at the output. Okay, so the output will produce FC plus FM plus FLO. Okay, this is the upper sideband, and we're gonna produce lower sideband, okay, at the output. And since FLO is same frequency as the carrier frequency, okay, so what happens is that this is becomes FC, this is FC. So FC plus FM plus FC, you're going to produce 2FC plus FM, which is high frequency. And another one is FC plus FM minus FC. So you're going to produce output FM. And this is the frequency that we want actually, which is the input message frequency, the original signal frequency. So we want to select this actually. So what we can do is we can use a low pass filter in order to remove the high frequency signal. Okay, so we can use a low pass filter to select only the lower frequency. Okay, we only select the lower frequency, and therefore we're going to produce the output VMT at the output. Okay, okay, so after this is about receiver parameters. Okay, so I will show you again. Okay, where are we now actually? So again I redraw the receiver, because receiver and similar with transmitter, there are many other processes involved inside it. Okay, so up to this slide about demodulator, actually we are learning about the demodulation process, which is the we can say that the last process happens inside the receiver. Okay, this is the receiver, and starting from this slide, okay, it shows about the tune circuit or the filtering process in the tune circuit. So starting from this slide, it is actually explaining about the front process. Okay, so over here the front process here is consists of tune circuit. Okay, so tune circuit consists of filters and amplifier. Okay, so what is the purpose of tune circuit actually? Okay, so if you see from this receiver, this antenna receive many signals. Okay, there are many input signals absorbed by the antenna, but actually we don't want all the signals. We only want to select the desired signal. For example, if I want to listen to a radio station, for example, Hot FM, for example, so I tune to that frequency, the Hot FM frequency. Okay, when I tune my radio to that Hot FM frequency, that means I giving the instruction to the tune circuit to tune to the center frequency of the Hot FM. Okay, so when we tune our radio, actually we are tuning the tune circuit. Okay, we are tuning the tune circuit, and the tune circuit will tune to the, for example, X frequency. Okay, X hertz, for example. So these X hertz, when you draw the spectrum, it is center at X. Okay, this is F. Okay, when I tune to a radio station with X hertz frequency, okay, actually the tune circuit will resonate at X frequency, and we only select this frequency band. I will use a different color. Wait, I'll try my best to make you understand. Wait, what happened? Okay, so I use a different color. So for example, here is the wait, so I want to show you what happened actually. Sorry, I redraw again. Sorry, I want to explain about this. For example, the frequency band, this is a frequency band F of hertz. Okay, so the antenna absorb all frequencies, many frequencies, to the receiver, but we don't want this. We don't want this frequency band. So I want to listen to a radio station, for example, Hot FM with X frequency hertz. Okay, and what happened is that this tune circuit will tune at, for example, X hertz of this radio station. So this is, for example, for Hot FM. Contoh, example, Hot FM radio station. So tune circuit will resonate at X frequency. What happened is that it will select only a certain portion, a small portion of the bandwidth to be processed within the receiver. So the tune circuit will limit the amount of bandwidth, the amount of frequency signals that we receive from the antenna. Okay, so how to do that? That means tune circuit needs to have filters. Okay, so now starting from this slide explain about the receiver parameters, which is actually referring to the filters inside the tune circuit. Okay, so from here we're going to see the first parameter is selectivity. Selectivity is the parameter to show the ability of the receiver to select only the desired frequency band and remove the other frequencies. Okay, so the ability to select, okay, to select only the desired frequency, that one is the ability of filters inside the tune circuit. Okay, so there are parameters for the selectivity. The first one is what we call as the shape factor. Shape factor defined as bandwidth of minus 60 dB divided with bandwidth of minus 3 dB. Okay, so this is hertz. Hertz divide with hertz. So no unit. Okay, there's no unit for the shape factor. Okay, so this is a hertz divide with hertz. So no unit. Okay, so if you see from here, bandwidth of minus 60 dB and bandwidth of minus 3 dB. So this is actually referring to the filter parameters. Okay, and how does the bandwidth of minus 60 dB and how does the bandwidth of minus 3 dB looks like? So in order to understand this, we need to see the filter transfer function, okay, which is this one. Okay, I skip one slide to show you about this. Okay, so if you see from this graph, the bell shape here is the frequency response curve of the filter in tuned circuit. Okay, so this is the frequency response curve of filter inside the tuned circuit. And you see that the bandwidth, the minus 3 dB is starting from here. Okay, minus 3 dB. Okay, so minus 3 dB, this cross at this point, cross at this point. Okay, so for your information, ideally we want a filter that has a very sharp cut-off frequency. Ideally, okay, ideally we want the filter to select only this one, ideally, okay, so that we can get the range from F1 from F2 and we can remove the others. Okay, but in the real world there's no filter that can do this kind of cut off. There's no practical filter that can do very sharp cut off like this. Okay, instead a real filter will have a slope. Okay, it will have a slope like this. Okay, and when we want to design a filter, actually we want to design a filter that has a very sharp slope. Okay, very steep slope. Okay, the steeper the slope would be better. Okay, the steeper the slope would be better. Why? Because we can remove the other frequency. We want to remove the other frequency. Okay, and if you see from this frequency response curve, minus 60 dB is somewhere over here. Okay, somewhere over here. So it crossed at this point and at this point. This is minus 60 dB. And we have here, for example, F3, and here is, for example, F4. Okay, so that means bandwidth of minus 3 dB. Okay, bandwidth of minus 3 dB divide with bandwidth of minus 60 dB. So this is, you can see that this is F2 minus F1 divide with F4 minus F3. Okay. Divide with F4 minus F3. Okay, so that means we want, okay, we want the shape factor to be as close as possible towards the value of 1. Okay, we want the frequency response curve to have a shape factor close to 1, so that it is close to minus 3 dB cut off. Okay, very close to minus 3 dB cut off. That is the ideal case. Okay, so if the value is closer to 1, it will be better. Okay, so if you want to make a shape factor in terms of decibel, of course you can make shape factor in terms of decibel. So you can do a 10 log SF. Okay, you can get the value in terms of dB. Okay, and then what? There's another parameter. Okay, there's another parameter, what we call the bandwidth of the tuned circuit. Okay, which is equal to resonant frequency divide with the quality factor. Okay, what is this actually? Okay, so this is actually referring to the bandwidth of the tune circuit. Okay, bandwidth of the tune circuit. So how much bandwidth does the tune circuit will select? Okay, again this is also referring to the frequency response curve. Okay, frequency response curve. So we want to know how much is the bandwidth, okay, able to be selected by the tune circuit. Okay, what is the resonant frequency? FR. Resonant frequency is the center frequency. Okay, the center frequency. Okay, center frequency. So bandwidth, this one. Okay, so bandwidth in terms of hertz. Okay, Q, qualitative parameter of the tune circuit, does not have a unit. Quality factor is equal to inductive reactance divided with resistance of the tune circuit. So this is ohm divided with ohm, so no unit. Okay, so inductive reactance, this inductive reactance, this is not XL. XL is the size of a shirt. Okay, dia bukan size baju. So this inductive reactance is 2 pi F resonant L multiplied with inductor, or omega L. Okay, so okay, normally we when we ask about the selectivity parameter, we normally ask about the Q factor. Find the Q factor. Okay, so find the Q factor. So you need to know the inductive reactance divided with the resistance. So there's gonna be an example about this later. Okay, and then what? Sensitivity. This is the second parameter. Again, sensitivity also referring to the tune circuit in this example actually. So sensitivity is the ability of the receiver to detect the minimum RF signal. Okay, the ability of the receiver to detect the minimum RF signal. Okay, why? Because when the signal goes through the medium from transmitter to the receiver, it will have many times of attenuations, and when the signal arrives in the receiver, the amplitude will be lower, much lower, because of the attenuation process due to the distance and obstacles with in the medium. Okay, so the ability of the receiver to detect as minimum as possible amplitude of the input would be better. Okay, not only to detect, but it can do the demodulation to produce the original signal at the output. Okay, so not only to detect the minimum RF signal, but to detect and demodulate with a good quality at the output. Okay, dia bukan hanya detect, tetapi boleh juga memproses input yang mempunyai amplitude yang kecil ini menjadi output dengan kualiti yang baik. Okay, so sensitivity also called as the receiver threshold. Okay, how much is the minimum RF amplitude that can be detected by the receiver? So normally the threshold is defined as in terms of power in decibel. Okay, how much power, how much minimum power can be detected by the receiver. Normally we mention in terms of power. Okay, power in terms of decibel. The third parameter is bandwidth improvement factor. Okay, so bandwidth improvement factor is equal to bandwidth of RF divided with bandwidth of intermediate frequency. Okay, bandwidth of RF divided with bandwidth of intermediate frequency. Okay, So the bandwidth of RF is here defined as the bandwidth at the input of the receiver, okay, which absorbed by the antenna. So how much is the bandwidth bandwidth of the signals arrive from the antenna, which is very big, okay, and then we reduce the amount of bandwidth to become smaller. And bandwidth of intermediate frequency, what is intermediate frequency? Okay, so I will explain to you about intermediate frequency. So when we want to understand about intermediate frequency, first we need to draw the spectrum so that you can have a better understanding about the process happens. Okay. So remember, in transmitter, in receiver, we receive the AM signal. Okay, we receive AM signal. For example, we receive double sideband full carrier. Okay, we receive double sideband full carrier. So if you see from here, a double sideband full carrier, and also other types of signal that we receive from the antenna. Okay, so this is center at FC, FC plus FM, FC minus FM, and another frequency spectrum from other type of signals, okay, that we receive. So in order to do the demodulation, remember demodulation is the last process to produce the signal to produce an output signal with frequency FM. This is our target. Okay, our target is to produce the original signal with frequency FM. So how does the receiver do the conversion? Okay, so it is not directly convert into FM. Instead, it will change into intermediate frequency. But before we change into intermediate frequency, there's a tune circuit which only select the, remember that previously we have the tune circuit. So tune circuit will select this one. Okay, before that, before that we can calculate the bandwidth of RF over here. So this is the bandwidth of RF. Okay, the amount of signals, the amount of bandwidth received from the antenna. Okay, and then it goes through the tune circuit. Tune circuit will limit, for example, up to here. Okay, tune circuit will limit up to here, and it will select this. And then what? So when tune circuit select this amount, this portion of bandwidth, and then it will pass through the down mixer converter section for down conversion. So what happens is that it will do the down conversion of frequencies. So we're gonna produce intermediate frequencies. Okay, so this is F intermediate center. Okay, and then we're gonna produce FIF USF, upper side frequency, and then here is lower side frequency, FIF LSF, or you can say that lower and upper sideband. Okay, so from this selected by the tune circuit, it's gonna down convert the frequency band into intermediate frequency. After it down convert the frequency into intermediate frequency, then the receiver will do the demodulation process to produce the original frequency, which is FM. So the process of demodulation does not happen straightforward. Okay, so the frequency needs to be down convert into intermediate frequency pertengahan, and then we can do the demodulation to the to produce the lower frequency, which is FM. So this is the process inside the receiver. Okay, there's an intermediate frequency, frekuensi pertengahan. Dia tidak lompat terus kepada FM. Okay, so what is the bandwidth of IF? Bandwidth of IF is this one. Okay, a smaller portion of bandwidth that has been selected. Okay, bandwidth of IF. Okay, and then so you see that bandwidth of IF, so bandwidth of IF is lower than bandwidth of RF. Okay, so that means the smaller the bandwidth of IF would be better. Okay, lagi kecil nilai bandwidth IF, lagi bagus. That means the improvement gonna be increased. Okay, if the IF bandwidth lower, we gonna increase the bandwidth improvement, which is very good. Okay, and this bandwidth improvement can be expressed in terms of decibel, which is become what we call as an NF improvement. So 10 log of bandwidth improvement, so you're gonna get in terms of decibel. Okay, so ideally we want bandwidth improvement to be as high as possible. Why? It is stated here, reducing the bandwidth will reduce the noise power. Remember the noise power? Noise power is equal to KTB. Okay, if we reduce the bandwidth, that means we're gonna reduce the noise power, which is good. Okay, so this is the bandwidth improvement factor. So later you're gonna see that how does the receiver do the conversion from RF to IF to FM. Okay, so before that maybe I can explain that this RF, the word RF here means radio frequency. Okay, before you confuse, so I further explain. So this RF is referring to the radio frequency. What radio frequency is this? This is the AM radio frequency. Okay, AM band. What is AM band? AM band, as I mentioned previously, the frequency is around 500 something. Sorry, I forgot the exact value. 500 something kilohertz until 17 something kilohertz. Okay, so around 500 kilo until 1.7 megahertz. This is the AM band, AM frequency band. What is AM frequency band? AM frequency band consists of frequency for the radio station that I want to listen. Okay, so this AM band consists of many radio stations. Radio station A, B, C, D, and so on. Okay, so this radio station is within the AM band. Okay, so AM is under the category of radio frequency, and remember that AM is within the medium type of frequency. Okay, AM ini dalam julat medium range frequency. Medium range frequency. So this medium range frequency you're gonna learn in chapter 1 if you remember, medium frequency. Okay, so later you're gonna see what happened to the IF. So IF is around 400 something kilohertz, lower than the RF. Okay, we're gonna see that later. Example, let's do the example. Okay, example 2.1. So this is about the tune circuit. Again I draw the picture, So tune circuit is at the front side of the receiver. Okay, tune circuit. Okay, So this example, a high quality tuned circuit is used to keep the bandwidth narrow to ensure that only the desired signal is passed. Assume that a 10 microhenry coil with a resistance of 20 ohm is connected in parallel with the capacitor 101.4 picofarad. Okay, variable capacitor. So calculate the parameters. So that means here is you are given a resistor and we have the inductor which is connected in parallel with the capacitor. Okay, so this is L, C, this is R. Okay, so this is the tuned circuit. Okay, this is the tuned circuit. Okay, so what's the question? The first question asks, this is the first question, calculate the resonant frequency. Okay, resonant frequency Fr. How much is Fr? So that means this tuned circuit resonate at what frequency? What is resonant frequency actually? Apa sebenarnya resonant frequency? So the issue is like this. When you want to listen to a radio station, you tune your radio to that specific frequency. So that specific frequency is actually the resonant frequency. So when you tune to that frequency, you are actually giving instruction to the tune circuit. Tune circuit, please resonate at this frequency. Okay, so that means what happened to the spectrum? So tune circuit will resonate at the given frequency that we tune. When we tune our radio, it will resonate at that frequency. Okay, and select the bandwidth, small portion of bandwidth, and the resonant frequency is the center. Okay, resonant frequency located at the center of the selected bandwidth. Okay, resonant frequency ini berada pada center daripada bandwidth yang terpilih, yang dipilih oleh tune circuit. Okay, so resonant frequency is located at the center of the selected frequency band by the tune circuit. Okay, so now here is the solution is already been given. Okay, so resonant frequency is equal to 1 over 2 pi multiplied with square root of LC. Okay, so L is 101 point, how much? 1010 sorry, L is 10 micro. Okay, L is 10 microhenry. The capacitor is 101.4. Okay, so if you put inside here 10 micro and here is 101.4 picofarad, is it picofarad? Okay, pico, you will get maybe some 4 point something if I'm not mistaken. So the answer here has been rounded up to 5 megahertz. Okay, for simplicity, the answer here has been rounded up to 5 megahertz. So actually you're gonna get around, if I'm not mistaken, 4 point something. Okay, you get, and then it has been rounded up to 5 megahertz. Okay, but in the exam you don't round it up like that. Okay, dalam exam jangan buat bundarkan seperti itu. You do the exact answer. Okay, so this is just for learning process, so that easy to do the calculation. Okay, and then the second question asks about what if the inductive reactance, which is 2 pi FL. 2 pi FL. What is the F? F is the resonant frequency. Okay, so 2 pi multiplied with resonant frequency that we get from the previous question, and then multiplied with 10 microhenry. So you will get 314 ohm. Okay, you can use your calculator. Try to use your calculator. Boleh, if you don't understand, please ask. Okay, otherwise I will move to the next question. Kalau tak faham, tolong tanya. Okay, please ask question if you don't understand. So, the next question asks about selectivity of the tuned circuit. Okay, remember selectivity, previously we have the shape factor, we have the bandwidth of the tuned circuit, we have the quality factor. So which one actually? So in this example, it is referring to the Q parameter. Hello?
Hello, Doctor.
Yeah.
Yeah.
Pardon?
What question? I need one more. First question. What is the inductivity, reductance, reactance?
Sorry, can you
Yeah.
please repeat again the question?
This one.
Which one?
Question one. Question one.
Question 1.
Answer one. I mean answer one. Answer one. Yeah.
Okay. How much you get?
How can I get the quality? I mean the total number of 2 pi.
So how much you get? So first of all, you need to find the LC. So my suggestion is 10, this one, so 10 micro Henry multiplied with 101.4 picofarad. Okay, so you multiplied both of these first. 10 micro multiplied with 101.4 pico. Okay, I get 1.014 times 10 power of minus 15, and then I do square root of answer. Okay, I get 3.1843. Okay, then I multiplied with 2 pi. Okay, 2 pi, I multiply with 2 pi, I get 2.0 multiplied with 10 power of minus 7. And then 1 divide with answer, so I get 4998056. Okay, 4.998 megahertz, so it has been rounded up to 5 mega. Am I answering your question?
Yeah, Doctor.
Okay, so first of all, you need to calculate this one first. Okay, and then square root, you multiplied with 2 pi. 2 pi, from my calculator, it is shift and then x 10 power of x here. So I press shift, I press this button, times 10 power of x. So I get pi over here. I don't know your calculator, you need to find the where is the pi. So you multiplied with pi, 2 pi, and then 1 over the answer. Okay, so it gets 4.998. So it becomes 5 megahertz. Okay, and then the second question, inductive reactance, 314 ohm, 2 pi multiplied with resonant frequency multiplied with the inductance in Henry. Okay, so this inductance is in terms of Henry, so 10 microhenry. Okay, so you get 314 ohm. So the next question asks about what is the selectivity of the circuit. So the selectivity, as we learned previously, it has the bandwidth of the tuned circuit, it has the shape factor, it has the quality factor. So which one actually? So in this example, it is referring to the quality factor. Okay, so don't worry, normally in the exam we will explicitly ask the exact parameter. If we want you to find the quality factor, we will ask you to find the quality factor. But in this example, it is referring to the Q parameter. Okay, so Q parameter is equal to inductive reactance divide with the resistance. Okay, that means this is from here, from 314, divide with R. R is given in the question, which is 20 ohm. Okay, so that means 314 divide with 20, so you get 15.7. Okay, no unit. Be careful. So in ECS, make sure that you put the unit. If the parameter has a unit, you need to put the unit. Okay, for example, like this. Okay, if you don't put ohm, your answer is wrong. So be careful about that. Okay, so in this case, Q parameter or selective, which is a selectivity parameter, don't have the unit. Okay, then what? The question asks, how much is the bandwidth of the tuned circuit? How much is the bandwidth selected by the tuned circuit? How much is the bandwidth that has been selected by the tuned circuit? So bandwidth is equal to resonant frequency divided with quality factor. So this formula is from the previous slide, which is this one. Resonant frequency divided with quality factor. Okay, so resonant frequency divided with quality factor, that means 5 mega divide with 15.7. Okay, so 5 mega divide with 15.7, so you will get 318.47 kilohertz. Okay, wait. If you have question, you can ask. Okay, so this is the bandwidth of tuned circuit. So this is only this is the portion of bandwidth selected by the tuned circuit. Okay, that means if you draw the spectrum again, okay, so this is the bandwidth, which is equal to 318.47 kilohertz. Okay, and then what? Find the upper and lower cut-off frequency of the frequency band selected by the tuned circuit. Berapakah nilai frekuensi tertinggi dan juga frekuensi terendah yang telah dipilih oleh tuned circuit? How much is the upper frequency and lower frequency? Okay, so that means the question asks, how much is this one, F lower, F1, and the highest frequency, F2? How much? We know the distance, we know the difference here is 318.47, but we want to know how much is F2 and how much is F1. What is the upper and lower? Okay, so from here, you see that in this example, it divides the bandwidth into 2, so that what? Sorry, I redraw again. I redraw again. So actually like this. Resonant frequency at the center, and this is the bandwidth. Okay, so resonant, this is F. Let's say this is mega. Okay, so resonant frequency over here, FR. Okay, and we already know that the distance here is the bandwidth. We already know the bandwidth is 318.47 kilohertz. So in the solution, we divide the bandwidth into 2. Okay, we divide the bandwidth into 2, so that we can get half of the distance, half of it, so that we can add or subtract from the resonant frequency. So kita bahagikan dua supaya kita boleh tambah dan tolak daripada resonant frequency. Okay, so when we divide the bandwidth into 2, we get 0.159 megahertz or 159 kilo. Okay, so half of this we can add and subtract from the center. because we already know the center, we don't know the upper and lower limit. Okay, so when we want to find the upper limit, we just add the value, the half of the bandwidth with the resonant frequency, so that we can get the upper bound. F, the center, the resonant at the center plus half of the bandwidth, so we get the upper limit, 5.159. Okay, so that means 5.159. And then the lower limit is center minus half of the bandwidth, which is 5 divided with 5 minus 0.159. So we get 4.841 megahertz. So 4.841 megahertz. Okay. So this is just mathematics. We divide with 2 so that we can get 1. So from there we can add or minus with the center of the frequency. Okay. Do you have any question to ask? You can ask now. If you have question, you can ask. Otherwise, I will move to the next slide. Okay, kalau ada soalan boleh tanya. You can ask question. Okay, so no question. So if there's no question, I move to the next slide. Boleh Kalau tak ada soalan, saya teruskan. Okay. Okay, so where are we now? The AM receiver, the type of AM receiver. What is this actually? So this slide, okay, starting from this slide, the lecture notes explain about the type of whole receiver system. Okay, so now the slide shows about this type of receiver, the type of receiver. Okay, so we want to see from the whole picture. Okay, the whole picture of the receiver. So there are two types. There are two main types of AM receiver. The first one is about tuned RF receiver. Okay, so this is one of the oldest receiver type, TRF, which is tuned RF receiver. It is simple. It is simplest limit to single channel low frequency application. It has a high sensitivity and it has a few disadvantages. For example, the bandwidth is inconsistent, which varies with the center frequency when tuned to over wide range of input frequency. It is unstable due to large number of RF amplifier, and the gain is not uniform. Okay, so how does the tuned RF receiver looks like? It looks like this. So if you see from here, from the input, we have the antenna coupling networks, and then the input will be amplified a few times for 3 times here. Okay, and you see that so this is you see that the dotted line here. So and then here, this is also part of the tune circuit. This is part of the tune circuit which tune to the same frequency. So this is what we call as the RF section. Okay, where the tune circuit is within this RF section. So this is actually the tune circuit and also the amplifier together. Okay, and then what? And then it will do the demodulation. So this is the detector section. For both of these, detector section. So this is audio detector will do the demodulation process. Audio amplifier will amplify the output from the demodulation to the speaker. So we get the original output at the speaker, okay, to the speaker. So the process is very simple. You see that there's no down conversion to intermediate frequency. Okay, there's no down conversion to the intermediate frequency, and this is the simplest kind of receiver process. Okay, but it is not widely used. Okay, it is not widely used in the commercial radio. Okay, for the tune RF. Tune RF is not widely used in the commercial radio. Okay, it is only used for a specific application. And if you want to know about the one of the famous receiver type, okay, or the commercial commercial receiver type, it is called as the super heterodyne receiver. Okay, so this is the second type of receiver, which is super heterodyne receiver. Okay, so first we have the TRF, tune RF. The second is super heterodyne receiver. So this is one of the most popular AM receiver type. Okay, so the word heterodyne, okay, comes. This is a, if I'm not mistaken, this is a Latin word which shows about a mixing of two input. Okay, so heterodyne means mixing. So that means this receiver accepts more than two, at least two inputs, in order to do the processes. Okay, so super heterodyne consists of, so before I explain about this, so let's look about this one. So this is the super heterodyne receiver. Okay, so we have how many section? RF section, we have the mixer converter section, intermediate frequency section, and detection section. Okay, so we have 1, 2, 3, 4 sections. 4 sections. So RF sections consists of pre-selector, which is the tune circuit. Pre-selector is the tune circuit, which only select a portion of the bandwidth received by the antenna, and then we amplify the input. Okay, we amplify the signal. Okay, so over here, that means if I draw the spectrum, so over here, that means here. So when we tune our radio to a specific radio frequency, that means we're going to tune at the resonant frequency. So that resonant frequency is actually referring to the carrier frequency that we send from the transmitter. Okay, so if I want to listen to radio station X, I tune to X frequency. That X frequency is actually the carrier frequency transmitted by the transmitter. Okay, so this is the F USB that you have learned previously. This is the F LSB that you have learned previously. Okay, so how much is the frequency actually? So the frequency is actually around okay, so this F LSB, F carrier, F USB, it is within the AM band. Okay, it is within the AM band. Okay, within the this one 5xx until 17 something. Okay, kilohertz. Okay, so this, it is within the radio frequency band. And then what? Mixer converter will down convert the frequency into intermediate frequency. Okay, it will down convert into intermediate frequency, which is FIF center. Okay, this is FIF upper side frequency and FIF lower side frequency. And then what? IF section has a sharp band pass filter, which will select only a single channel. Okay, so you will select a single channel. Okay, you will select a single channel, and then you amplify the output. Then we can do the demodulation process. Okay, so this is FIF center. Later I will show you. Okay, so we only select in IF section. We only select a very small, only single channel. Previously, here we have more than one channel, but in the IF section we further select the bandwidth to become only a single channel, because when we want to listen to a radio station, we cannot listen to more than one radio station simultaneously. Okay, kalau saya nak dengar radio, saya tak boleh dengar 2-3 radio serentak. Saya kena dengar satu persatu. I want to listen to radio station X, so that means I need to listen to X radio station. I want to remove the others. Okay, so that means the band pass filter here will only select that single frequency channel so that I can listen to that radio station. Okay, and then after that it will do the demodulation process to produce the original output sine wave. Okay, so you see that here we have okay, so let's begin with the first one, RF section, which consists of tune circuit or the preselector. So this preselector or the tune circuit is gang tune, which is it is tuned to the same frequency as the local oscillator. So that means when you tune to different frequency, the local oscillator frequency also will change. Okay, because why? Because we're gonna insert the same tune, the same resonant frequency over here, similar with the frequency in the preselector. Okay, and then we're gonna amplify. So amplify provide initial gain and selectivity to minimize the radiation of local oscillator through the receiver antenna. And then what? Mixer converter section. This one. Okay, before that, for your information, we haven't asked in the exam about this block diagram. Okay, we haven't asked the student to explain the process happens in each section. Okay, belum pernah ditanya lagi soalan menerangkan proses yang berlaku dalam setiap section. We haven't asked that yet. Okay. Okay, I will begin with so we already begin the RF section, which will select only a portion of RF bandwidth received from the antenna. Now the signal pass through the converter. So mixer converter will down convert RF frequency band into intermediate frequency band. And when we down convert, the bandwidth will be preserved. Okay, so how does the conversion looks like? Okay, so conversion can be done by using here we have the mixer, which will mix both input, the input from the RF section with the local oscillator frequency. Okay, so you see that this is an X symbol. That means it will do the process of multiplication in time domain. When you multiply two input, you're going to produce upper and lower, and also the harmonics. Okay, so you see that here the output here consists of Fi, Fo, the upper frequency, and also the lower frequency, Fo minus Fi or Fi minus Fo. Why odd here? Because we want to make sure that the frequency is positive. So if local oscillator frequency is higher, that means we need to use Fo minus Fi, or Fi minus Fo if the F input larger than the local oscillator frequency. Okay, and you see that after that we can use filter only to select the which one we like, the upper frequency or the lower frequency side. Okay, we can select that one. So if I draw again the picture, again I always draw this so that you can have better understanding. Okay, so imagine that here is the FRF selected by the pre-selector. Okay, so here is actually the resonant frequency or the carrier frequency, and then here we have FUSB, here is FLSB. Okay, this is the RF from the RF section, and then it goes through the mixer converter section. So mixer converter section will down convert the frequency into IF frequencies. Okay, so every RF component will be translated into lower frequency. So in my example here, I have three component, 1 2 3 component of RF frequencies. That means it will down convert all of this 1 2 3, okay, into intermediate frequency, which is FIF center, FIF USF, upper side frequency, or you can say upper side band is similar. Okay, in Wayne Thomas's book it used the parameter of USF and LSF. So here is FIF LSF, LSF, lower side frequency or the lower side band. Okay, and the bandwidth remains the same. So mixer converter does not change the bandwidth, it's only down convert the frequency. Okay, so it said that here local oscillator is designed so that its frequency is always above or below the RF carrier by amount of equal to intermediate center, by an amount equal to IF center frequency. So the amount of FLO, local oscillator frequency, must be designed correctly so that it is tuned to the desired frequency. Okay, so how much is FLO? So that means FLO, local oscillator frequency, can be higher or lower than the range of RF frequencies. Dia boleh local oscillator frequency boleh jadi lebih besar atau lebih kecil daripada range of RF frequencies. Okay, and you see that it is stated here that normally most of the time local oscillator frequency is higher than the range of RF frequencies, so that we can do the because up conversion leads to a smaller tuning range, so that we want to produce a smaller tuning range. Okay, much easier to design the oscillator that tunable to a smaller radio frequency. So this is one of the reasons that why we choose FLO frequency larger than the FRF. So if mixer and LO are in a single stage, it is called converter. So we are actually referring to the converter, only single stage down conversion. And most common IF center, so this is actually referring to the center of IF, which is 455 kilohertz. So the mixer converter is designed in such a way that it will down convert the RF frequency to intermediate frequencies center at 455 kilohertz. This 455 kilohertz is a standard value for the center of IF, which is a factory tune. So that means by standard we are using 455 as a center frequency of the intermediate frequency band. Okay, so that means FIF center here is actually 455 kilohertz. By standard it is like this. Okay, and this 455 is a standard value, and it is selected, this value is selected as a standard because for this one so that we can have an adequate selectivity to design a sharp bandpass filter in the IF section later. Okay, and center frequency is fixed. Okay, that means the 455 kilohertz is fixed and factory tuned. Factory tune means that when we buy the equipment, the component, electronic component, it is already set from the factory that the center of IF gonna be 455 kilohertz, which is according to the standard AM. Okay, so if we generalize this center frequency to be equal to all components, we can effectively suppress the adjacent channel interference. Okay, we can effectively suppress the channel, the next channel, the adjacent channel, from becoming the interference to our signal. Okay, so these are the reasons why the number 455 is selected as the standard for the center of IF. Okay, and here is the terminology for the frequency values. So if the local oscillator, okay, if the local oscillator larger than the radio frequency, okay, we call it as high side injection. Okay, if the local oscillator frequency larger than the radio frequency, we call it as high side injection. And if the local oscillator is lower than the radio frequency, we call it as low side injection. Okay, so high side and low side injection is just a terminology to describe the frequencies, the frequency band of the local oscillator and also the RF. Okay, so what we need to find, we can find the IF. Okay, we can find the IF using this parameter. Okay, from the high side or low side injection, we can find the FIF. So for example, for high side injection, FIF is equal to FLO minus FRF. Okay, for here, FIF for the low side injection, it is equal to FRF minus FLO. Okay, and so this is what it means by the high side and low side injection. So I already answered this question in the notes. That means high side injection means local oscillator larger than radio frequency, while low side injection means that the local oscillator frequency is lower than the radio frequency. Okay, and for your information, most of the time in the practical case, we use the high side injection. Okay, as stated in this statement. Okay, so this statement is actually referring to the high side injection. Okay, high side injection is more preferable compared to the low side injection. Okay. Okay, so okay, wait. So from here, mixer converter. So I flashback a few slides. So mixer converter already down convert into intermediate frequency. Okay. Now what? Now it will go through the IF section. IF section will only select a single frequency component. Okay, IF section will select only the single frequency channel and then amplify it so that we can do the demodulation process in the detector section. Okay, so IF section here consists of bandpass filter and also the IF amplifier. So bandpass filter in the IF section will select only a single frequency channel, and then it will go through the IF amplifier to amplify it, okay, so that we can do the demodulation process in the detector section. So detector section consists of demodulator or detector, which will recover the original signal by doing the demodulation process, okay, and then we amplify it, okay. So if I flash back, okay, so that means IF section, it will select only the desired frequency band. For example, it will select this one, for example, in the IF section, okay. And then here we can do the demodulation process to produce the original frequency message, FM, okay. So IF section will select only single frequency channel. Then we can do the demodulation, okay. So after demodulation, we can amplify the output of the demodulator so that we can have a high amplitude output, and then pass through the speaker, okay. After this, pass through the speaker, okay, as shown in the this picture, okay. So complete process, okay. So that's how you should explain in briefly what happened in the RF section, what happened in the mixer converter section, what happened in the IF section, what happened in the detection section. Until last semester, we haven't asked about explaining about each process. Okay, kita belum pernah tanya lagi Okay. So maybe you need to see the example. This one I think in your notes there's no slide about this Tidak ada slide tentang ini is it? The notes that I sent to you in the author, does it have this slide or not? Anyone can respond? Student, are you still there? Could you please respond? Can you hear my voice?
Yes, Doctor.
Okay, thank you for the response. Because I'm afraid that I'm talking to myself. Okay, saya risau saya cakap seorang-seorang. Okay. So I'm not sure whether this is in your notes or not. Okay. But if it is not in your notes, no problem. This is taken from the Wayne Thomasis book. Okay, ini ada dalam buku Wayne Thomasis. The book is in the author. I already put the book in the author. Okay, so I just take one page from the Wayne Thomasis book about the super heterodyne receiver. Okay, so this is about super heterodyne receiver. Okay, so here we have the pre-selector. Okay, we have the pre-selector, and then we have the mixer converter section. Okay, pre-selector is the RF section, and then here we have the mixer converter section, and then we have the IF section. Okay, we have up to the IF section. Yes? You have question to ask?
Yes, Doctor.
Tak dengar? You asking question or not? Okay. Sorry, I hear a voice previously. I thought you want to ask question Ada soalan nak tanya sebenarnya. Saya tak pasti. Okay. So again, can I get your response? Are you still there, student? Can you hear my voice?
Yes, Doctor.
Okay, thank
Yes,
you for the
Doctor.
response. Okay, this is about super heterodyne receiver. This is example from the Wayne Thomas's book, and I take it from chapter 5 in the book, figure 5.5, which is chapter 5. So this is a super heterodyne receiver which consists of RF section, mixer converter section, and also the IF section. Okay, so you see that from the input to the RF section, which is the input to the preselector, from the antenna we receive this frequency band. So this is actually referring to AM frequency band. Okay, the one that I explained previously, 5 something something. So another standard of AM is from 535 until 1605. So AM has a few set of frequency band standard. AM consists of a few standard of frequency band. One of it is this one, 535 until 1605 kilohertz. Another one is from another one is until 17 something. So it consists of a few set of band according to different countries. So different countries might have a different set of frequency band. Okay, but the difference is not much, only a few kilohertz difference according to different region of countries. Okay, so the antenna receive very big bandwidth like this. So in this example, we want to tune to channel 2, which is located at 550 kilohertz. Okay, for example, I want to listen to radio station 2. The frequency is 550 kilohertz. Okay, and this tune circuit will tune to that frequency at 550. So when I tune at 550 kilohertz, that means the preselector will have center frequency at 550. Okay, when I tune my radio at 550, I'm actually instructing the preselector to select frequency band center at 550 kilohertz. Okay, and this preselector has a bandwidth of 30 kilohertz. Okay, the preselector has a bandwidth of 30 kilohertz. Okay, so that means okay, it will center at 550 and the range here is 30. Okay, 30. Sorry, I erase this one. Wait, Okay, so within this 30 kilohertz, there's actually another radio stations. Okay, in this example, so back to this picture. So you see that when the preselector tune at 550 and it contains of 30 kilohertz of bandwidth. Okay, so in this example, this 30 kilohertz consists of another channels as well. Okay, and according to this example, each channel has a bandwidth of 10 kilohertz. So if one channel is 10 kilohertz, that means this preselector will select 3 channels. Okay, 3 channels. Previously from the antenna, maybe we have, for example, we have 50 channel, for example. Okay, so if wait, how much is it? 1605 minus 535. So we get 1070 divide with 10. So we're gonna have 107 channel. Wait, So if one channel is 10 kilohertz, I can get here is 1605 minus 535. So I get here 1707. Okay, 1707 kilo. And if I divide with 10 kilo for one channel, okay, and then I divide with 10 kilo, I gonna get 107. I get 107 channels. Okay, and after it goes through the RF section, it goes through the pre-selector. Pre-selector only select 30 kilohertz, which is 3 channel only. Okay, so we have channel 1 located from 535 until 545. Okay, channel 1. Channel 2 from 545 until 555 kilohertz, and then channel 3 555 until 565 kilohertz. So all of these 30 kilohertz. Okay, 30 kilohertz is the bandwidth of the pre-selector. So it depends on the pre-selector. How big is the bandwidth for the pre-selector? It depends on the pre-selector. Okay, in this example it is 30 kilohertz. Okay, so what? So actually I want to listen to this radio station only. I don't want channel 2 and I don't want channel 1 and channel 3. I just want to listen to channel 2. Okay, so what happened next? So it will go through the mixer converter section. Okay, mixer converter section. Mixer converter section will have the mixer converter will have the input from local oscillator, which has the frequency of 1005 kilohertz. And you see that this 1005 kilohertz is larger than the range of RF frequencies selected from the pre-selector. Okay, the pre-selector only select from 535 kilo until 565 kilo. So that means this is gonna be up conversion. Okay, high side injection. This is what we call as a high side injection, because FLO is larger than the FRF frequencies selected by the pre-selector. Okay, so mixer converter will down convert the RF frequencies into intermediate frequency. So how does the mixer converter down convert into IF? How? So we can use the high side injection. From the high side injection, we can find the FIF equal to FLO minus FRF. Okay, so every RF component will be converted into IF. Okay, so you see that from here we have the upper bound, the lower bound, and the center frequency. So if you see from here, we actually have how many? 1, 2, 3, 4, 5, 6, 7 component. Okay, if we have 7 component, that means we're gonna have 7 IF frequencies. Okay, so here in the example, it converts one by one. So for example, we convert the first RF, the lower frequency RF. So FLO minus FRF, so 1005 minus 535, so we get 470 kilohertz. And then the next one is 450, so 1005 minus 540 kilohertz, we get 465 kilohertz. And then 1005 kilohertz minus 545 kilohertz, so we get 460 kilohertz. So this is for channel 1. Okay, and then what? 1005 kilohertz minus 550, we get 455 kilohertz. Then 1005 minus 555 kilohertz, we get 450 kilohertz. And this is the channel 2. Okay, this is the channel 2. Okay, and then 1005 kilohertz minus 560, we get 445 kilohertz, and then 1005 kilohertz minus 565 kilohertz, so we get 440 kilohertz, and this is the frequency range for channel 3. Okay, so based on this calculation, we can see that what happened. Channel 1 will be located over here based on the IF values that we already calculate. Okay, so this is channel 1. Okay, you see that channel 1 becomes from range 460 until 470. 460 until 470. This is channel 1. And then channel 2 from 540 until 460. 540 until 460. So this is channel 2. Okay, channel 2. Channel 3. Channel 3 is from 440 until 450. From 440 until 450, this is channel 3. Okay, and all of this is the IF frequencies. Okay, above here is RF. Okay, so this is the IF frequencies. Okay, but it is not finished yet, because we still have a channel 1 and channel 3. I don't want to listen to channel 1 and channel 3. I only want to listen to channel 2. Saya cuma nak dengar radio number channel 2 sahaja. Okay, so I need to do further process. Okay, I only want channel 2. I don't want to listen to the others. Okay, so what? Now all of these will pass through the channel 1, channel 2, channel 3 will pass through the IF section. This one, IF section. So in IF section, remember we have the band pass filter and also we have the amplifier. So band pass filter, as I mentioned previously, it will select only the single frequency channel. So it will select only channel 2. And remember, the band pass filter in the IF section must have a sharp cutoff filter compared to the preselector. The preselector has a 30 kilohertz bandwidth. Now the IF bandwidth needs to have 10 kilohertz of bandwidth. So since I want to select channel 2, that means the band pass filter must have range of frequency from 450 until 460. Okay, so the band pass filter will select only a single channel. It's gonna have a bandwidth of 10 kilohertz. Okay, sharp cut-off frequencies compared to the preselector. Okay, so that means this band pass filter will have the center frequency at 455 kilohertz, and it has a bandwidth of 10 kilo. So after the IF filter, it's gonna produce only channel 2 at the output. Okay, so this channel 2 will goes through the IF amplifier. Okay, it will goes through the IF amplifier, and it will amplify the amplitude so that we can do the next process. And then from here, channel 2 will go, the amplified channel 2 will go through the detection section for the demodulation process to get the original output, which is at frequency FM. Okay, So there's another process. So after the IF filter, it's gonna be IF amplifier to amplify the amplitude of channel 2. Then it goes through the detection section to do the demodulation process to get the original frequency, and then we amplify it and then send to the speaker. So complete process. Okay. So do you have question to ask about this? Okay, so this is a good example to understand about the super heterodyne, the process inside the super heterodyne. Okay. So if you have question to ask, please ask now. Otherwise, I will move to the next slide. Okay. So no question? Are you sure? Ada soalan tak nak tanya? If you have question, please ask now, so that I can further explain about what I have said previously. If you don't have question, I will move to the next example. Okay, kalau ada soalan, sila tanya. Anda dialu-alukan untuk bertanya soalan. Okay, so no question, so I will move to the next example. Okay, again, this is also from Wayne Thomasis. Okay, from Wayne Thomasis' book, this is also about super heterodyne receiver. Okay, so this example also has been asked in the final exam in the sub question. We ask the student to find the intermediate frequencies. Okay, so for example, you are given the RF frequencies, you are given the LO frequency, local oscillator frequencies, so you need to find the IF frequencies. So this is from the picture, so that means we receive this one. So given the RF frequencies, this one, so we need to find the FIF frequencies after the mixer converter. Okay, given the local oscillator frequency is 1355 kilohertz. Okay, according to this example, 53. Okay, for an AM super heterodyne receiver that uses high side injection, that means local oscillator frequency larger than the RF frequencies. It has a local oscillator frequency 1355 kilohertz. Determine the IF carrier upper side frequency and lower side frequency for an RF wave that is made up of carrier upper and lower side frequency, which is this is the carrier frequencies, this is the upper side band and the lower side band of the RF frequencies. So find the IF. So since we have 3 components of RF, that means we're going to have 3 components of IF. Okay, so what we need to do is to convert one by one. Okay, we can use the high side injection equation, which is FIF equal to FLO minus FRF. Okay, so in order to find the center frequency of IF, we need to do FLO minus FRF center, which is 1355 minus 900 kilohertz, so we get 455 kilohertz. So if you draw the frequency band, it is actually like this. This is 900, this is 905, this is 895. Okay, and we need to convert into intermediate frequency. Okay, so this is FIF center, this is FIF USF, this is FIF LSF. Okay, lower side frequency. So we get 455 here for the center. Then what? We want to find the F upper side frequency. In order to find the upper side frequency, okay, we need to do FLO minus the FUSB of the RF. Okay, we minus with the upper bound of the radio frequency so that we can get the lower bound for the intermediate frequency. Okay, so 1355 minus 895, we get 460 kilohertz. Okay, then for the FIF lower side, we get FLO minus FRF USF, the upper bound of RF. So we get 1355 minus 905 kilohertz. So we get 450 kilohertz. Okay. So we have asked this question previously in the final exam as a sub question for chapter 3. Kita pernah tanya soalan ini, very simple. Okay, you just need to convert the given RF frequencies into intermediate frequencies. Okay, so you convert this one. You see that it's already been drawn here from 450 until 460 kilohertz. Okay, any question to ask? You can ask now. Otherwise, we will move to the next slide. Okay, if you have question, please ask. Otherwise, I will move to the next slide. Okay, so no question. So let's look into the next slide. Okay, let's look into the next slide. Image frequency. Okay, image frequency. This is also favorite question in the final exam. Okay, ini antara soalan favorite. So image frequency is any frequency other than the selected radio frequency carrier that if allowed to enter into the receiver, it will mix with the local oscillator and will produce a cross product frequency that is equal to the intermediate frequency, IF. So image frequency is actually a mirror to the radio frequency. Okay, it is a mirror to the radio frequency that we receive from the antenna. Okay, so that's why we need because we already know our local oscillator frequencies, and we need to control the amount of RF frequencies that we received so that we are not producing image. Okay, so image is here. Okay, so if the radio frequency is the center, if the radio frequency, the distance from radio frequency is for about FIF from the local oscillator, it will produce the image at the upper side of the local oscillator. Okay, and what happened? Okay, what happened if what happened if these things occurs is that the receiver will be unable to differentiate which one is the signal that received from the antenna. Is it this one RF or is it this one image? Okay, because both of these will produce the FIF. Okay, so it is the job of the pre-selector or the tune circuit to remove the image frequency. Ia adalah tugas pre-selector untuk memastikan image frequency tidak masuk ke dalam receiver. Okay, and the way we want to calculate the image frequency is F image equal to FLO plus FIF. This one, FLO plus FIF. Or F image equal to FRF from here, from FRF plus 2 times FIF. Okay, so we get the image. So this in terms of hertz. Okay, in terms of hertz. Okay, let's look in the example. Example 212. Okay, for the image frequency, about image frequency. Okay, so determine the image frequency for a standard broadcast band. Receiver using 455 kilohertz of intermediate frequency and tuned to the station of 602 kilohertz. Okay, so determine the image frequency. How much is F image? So you are given FIF and you are given FRF. So broadcast frequency, when you tune to a radio station, so this is actually FRF, which is actually referring to the F carrier. So when I want to listen to this radio station, I need to tune my radio at 620 kilohertz. Okay, so the center of the center frequency of the tuning range is at 620 kilohertz. Okay, so now the question asks determine the image. So we can actually find the image using any of the two equations given in the previous slide. Okay, in this example, it tries to find the local oscillator frequency first. FLO is located at FRF plus FIF. So we get 1075. So from FLO, we can determine the image located at FLO plus FIF, which is 1530 kilohertz. And actually you can find the F image using the other frequency, as using the other equation, which is FRF plus 2 times FIF. Okay, so you can use this one as 620 kilohertz plus 2 times 455 kilohertz. So you will get the same answer, which is 1530 kilohertz. Okay, so more simple if you use this equation, so FRF plus 2 times FIF. Okay, if you have question, please ask, otherwise I will move to the next slide. Okay, kalau ada soalan boleh tanya. Tak ada, kalau tak ada saya teruskan. Image frequency rejection ratio is the numerical measure of preselector ability to reject the image frequency. So this is a parameter to determine the ability of the receiver to reject the image frequency. Okay, so again, this IFRR is the favorite question that has been asked in the final exam. Okay, this gonna be this has been one of the favorite question, sub question in the final exam, to find the IFRR. Okay, so image frequency rejection ratio can be calculated using the parameter alpha equal to square root of Q square times rho square. Q is the quality factor of the tune circuit, rho is the rejection ratio. Okay, and I suggest you to make a bracket like this, so that you will not do the careless mistake. Okay, previously, based on the previous experience, students, many students do careless mistake in this part. I don't know why. Okay, So they make a careless mistakes for this. I don't know why they give the wrong answer at this part. So my suggestion to make a bracket so that you are not going to do careless mistakes in the calculation. Okay, so rho parameter is equal to F image divide with FRF minus FRF divide with F image. So hertz divide with hertz, so there's no unit for this parameter. Okay, so you can neglect this part. Just focus on this part. Okay, what is the Q parameter? Q parameter is equal to inductive reactance divide with the resistance of the tuned circuit. Okay, so this is supposed to be a subscript. So this is not a XL. XL here is the size of a shirt. Dia bukan size baju. So it is actually the inductive reactance. So L here is supposed to be subscript. Okay, small l is supposed to be like this, XL. Okay, so it is equal to F resonant divide with the bandwidth of the tuned circuit. Okay, and after this you can find the image rejection ratio in decibel. Okay, so you need to do 20 log alpha. Okay, 20 log alpha you will get IFRR in decibel. Normally we ask you to find in term of decibel. Okay, so let's look in the example. Okay, so this example is based on the previous example in 2.12. Okay, in example 2.12 we already calculate the F image, which is equal to 1530 kilohertz. Okay, and we already have the FRF is given in the previous example, which is the broadcast frequency, which is 620 kilohertz for the FRF. Okay, so we can find the image rejection ratio alpha. Okay, how to find it? So we can use this parameter. So first we need to find the rho parameter F image divide with FRF minus FRF over F image. Okay, so 1530 kilohertz divide with 62 kilohertz, and then minus 62 kilohertz over 1530 kilohertz. Okay, so you will get 2.0625. Okay, try use your calculator so that you can be familiar with the calculation process. Okay, and then what? You can find the alpha parameter, which is equal to square root of 1 plus q square rho square. Okay, so square root of 1 plus q parameter given from the question, okay, multiplied with the rho parameter, the rejection ratio that we have calculated. Okay, make sure both of it is a square, and then plus 1 and then square root. So you should get this amount. Okay, try use your calculator. Can you get this amount or not? Okay, if you cannot get this amount, please inform me now. Okay, kalau tak dapat nilai ni, tolong beritahu. So once we get the alpha parameter, we can find alpha parameter in terms of decibel. So that means we need to do 20 log alpha. So 20 log 82.5061, which is equal to 38.33 decibel. Okay, so this is the image rejection ratio. Any question you want to ask about this? Please ask question. Ada soalan? Kalau ada soalan boleh tanya. Okay, so if you don't have question, let's move to the next slide. Okay, so up to here we have finished the first part of chapter 3. Okay, we have learned about amplitude modulation. Now we want to look into angle modulation, okay, which is consists of frequency modulation and also phase modulation, PM. Okay. Angle modulation is for both FM and PM. You will see later that the frequency modulation and phase modulation are interrelated to each other. They are like a twin brothers which affected one another. Okay, so angle modulation for both FM and PM, the general equation is equal to Vt, which is equal to Vc sine 2 pi Fct plus theta t. Okay, and make sure that you make a big bracket here. Okay, because all of these belong to the sine function. Theta t is a function of modulating signal. Okay, theta t consists of modulating signal frequency. Okay, so theta t is a function of Vmt, and Vmt is equal to, as usual, equal to Vm sine 2 pi Fmt. Okay, and if you look from other literature books, so other than Wayne Thomas's, so because this slide is according to Wayne Thomas's book, so if you look from other literature books, they use cosine. Okay, they use a cos. Okay, cos. Wait, I erase. Wait. Some other literature book use cosine function. Similar with this one, they use a cosine. So no problem, doesn't matter. Okay. And another thing is that a careless mistake by the student, they tend to do like this. Vct is equal to Vc sine 2 pi Fct plus theta t. They do like this. No bracket. Okay. So what happen is that they will calculate one by one, this one and this one. So you're gonna produce the wrong answer. Okay. So that's why I suggest to the students to make a big bracket. Okay, the bigger the bracket will be better. Okay, lagi besar bracket lagi bagus. So that you are not going to do the careless mistakes. Okay, because if you do the careless mistakes here, there might be possibility that the rest of the question will be wrong. Okay, because the first part is to define the equation, then to calculate the rest of the parameters. And if you wrong in the general equation, there might be possibility that the rest of the questions you will give the wrong answer. Okay. Okay, so we want to now we want to see what is actually the parameter inside the sine wave, inside the sine function. Okay, we want to see about we want to learn about this this parameter. Okay, so theta t is what we call as the instantaneous phase deviation. Okay, instantaneous phase deviation is theta t. It is the instantaneous change of phase for the carrier at a particular time. Okay, kadar perubahan fasa pada masa tertentu. Okay, the unit is radians. Okay, the unit is radians. And then what? The second parameter is instantaneous phase. Instantaneous phase is omega ct plus theta t. Okay, which is all of this 2 pi fct plus theta t. So this is the instantaneous phase. Instantaneous phase is the precise phase of the carrier at a specific time. Okay, nilai sebenar fasa carrier pada satu-satu masa. Okay, again the unit is radians. Okay, so we have 1, 2, and then we have the third. The third parameter here is what we call as the instantaneous frequency deviation. Kadar perubahan frekuensi carrier pada masa tertentu. Okay, so this is defined as theta prime t, okay, which is equal to derivative of theta t d dt of theta t. Okay, so deviation of theta t, you're going to get theta prime t. Okay, pembezaan theta t, you akan dapat theta prime t. And if you want to get back the theta prime t, so theta prime t is actually equal to integral of theta prime t dt. Of course, if you do the deviation, you need to do the integral. Okay, so here you're gonna get theta prime t. The unit is in terms of radian per seconds, or cycle per second, or hertz. Okay, and then the fourth parameter is the instantaneous frequency, which is the precise frequency of the carrier at a specific time. Okay, so it is defined as the first derivative of omega ct plus theta t. So that means you are going to do the first derivative of d dt 2 pi f ct So I change omega into 2 pi f plus this is theta t. Okay, so it becomes like this. Omega c is 2 pi f c. Okay, two pi f c plus theta prime t. Okay, so the unit is radian per second or hertz. Okay, and it already been explained here, which is 2 pi f c plus theta t. So the unit is radian per second. Okay, and therefore the phase modulation can be defined as angle modulation with instantaneous phase blah 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 blah. Okay, so you see that phase modulation, PM phase modulation is defined as the process of changing the phase of the carrier in accordance with the amplitude variation of the input message. Okay, while FM, frequency modulation, is the process of changing the frequency of the carrier in accordance with the amplitude variation of the input message. Okay, so that's about the PM and FM. Another parameter is what we call as the deviation sensitivity parameter. Okay, deviation sensitivity parameter. So deviation sensitivity parameter consists of two, which is Kp and Kf. Kp and Kf. Okay, so Kp is the phase deviation sensitivity parameter. Okay, Kp is the phase deviation sensitivity parameter. Kf is the frequency deviation sensitivity parameter. Okay, so from Kp and Kf, actually we can define the theta t and theta prime t. Okay, so theta t is actually equal to Kp Vmt, unit in terms of radians, and then theta prime t is Kf Vmt, radian per second. Okay, where Kp and Kf are the constant parameter and are the deviation sensitivities for the phase and frequency modulator respectively. Okay, so deviation sensitivities are the output versus input transfer function for the modulators, which give the relationship between what output parameter changes with respect to the changes in the input. Okay, and Kp, the unit is radian per second. Okay, the unit for Kp is radian per second. It is calculated by subtracting by subtracting the theta values divide with the range of voltage values. So delta theta divide with delta V. Okay, delta means that a range of theta. That means if we have more than one theta, okay, so we can use like this. For example, theta 2 minus theta 1 divide with V2 divide minus V1. Okay, so we can get like this. So the unit is radian per volt. Okay, what about Kf, frequency deviation sensitivity parameter? So it is equal to delta omega divide with delta V. The unit is radian per second per volt. Okay, so you can calculate like this. So omega 2 minus omega 1 divide with V2 minus V1. Okay, and if you can put inside the theta t equation, which is theta t is the integral of theta prime t, so integral of Kf Vmt. So how does we get a Kf Vmt? Kf Vmt is given from the previous slide, which is this one, theta prime t. So you can do the integral of Kf Vmt. So since Kf is a constant parameter, since Kf is a constant parameter, we can put outside. So we can do the integral of Vmt dt, okay, over the time. Okay, so about the deviation sensitivity parameters, we have asked this in the previous final exam. Okay, we have asked to find this parameter. I'm not sure which one, Kp or Kf. So for example, Kf, find the Kf. So the question in the final exam, it gave a table of omega and also the voltage readings. Okay, so we get a few parameters. So we get here, for example, x1, x2, x3. Here is y1, y2, y3. Okay, so in order to find the Kf, so Kf is equal to delta omega divide with delta V. So this is x2 minus x1 divide with V2 minus V1. So V2 minus V1, or you can also select x3 minus x2 divide over V3 minus V2. So it can be any value with the adjacent value. Okay, dia boleh sebarang value dengan nilai sebelahnya. Okay, so it is a linear function. It is a linear function. That means you can use x2 minus x1 or x3 minus x2. Okay, so you can get this value Kf. Similar with Kp. If you are given Kp, if you want to find the Kp, that means you will be given theta. Okay, theta versus voltage. Okay, and then you can find the values. Okay, so this is a simple question. You just need to subtract the given values and divide with the voltage, so you get the deviation sensitivity parameters. Okay, so from here we can define the complete equation for PM and for FM. Okay, so kita boleh buat persamaan lengkap untuk kedua-dua modulation type ini. So from the general equation, okay, from the general equation, Vc sine omega ct plus theta t, okay. So again, I suggest make a big bracket, okay. So we can do the phase modulation parameter, phase modulation equation, phase modulation equation. We just need to replace theta t with the given parameters, okay. So we know theta t is kp vmt, okay, and this is kp vm sine 2 pi fm t, okay. So therefore Vc sine omega ct, so this is actually 2 pi fct, 2 pi fct plus kpvm sine omega mt, so this is actually 2 pi fmt. Okay, so we get the complete equation for the phase modulation. Okay. And then what? We can also find the frequency modulation equation. Okay. So given from the general equation of angle modulation, Vc sine omega ct plus theta t, we can replace theta t with integral of theta prime t. Okay, remember theta prime t, we get this by do the first derivative of theta t. Okay, this is theta prime t d dt of theta t. And if you want to find theta t, that means we need to do the integral process of theta prime t dt. Okay. So theta prime t, we get theta prime t is kf vmt. So this is given in the previous slide, which is this one, theta kf vmt. Okay, so we put inside kf vmt, okay, kf vmt, so vmt is vm sine 2 pi fmt. Okay, so this one you can put outside vm and kf because both of these are constant parameters. So integral of sine omega mt, so this is actually 2 pi fmt. Okay, so integral of sine, you will get negative cos over omega m. Okay, so therefore you get Vc sine omega ct minus kf vm over omega m cos omega mt. So you can also write like this, Vc sine big bracket 2 pi fct, okay, for the omega ct, minus kf vm over 2 pi fm cos 2 pi fmt, and then close big bracket. So in what I'm doing here is that I convert omega into 2 pi f. Okay. Okay, next. Exercise 3.1. Derive the PM phase modulation and frequency modulation signal using both cosine wave signal. So the question asks you to define the FM and PM equation using cosine. So you are given the general equation in terms of cosine and modulating signal in terms of cosine. Okay, so normally even in the exam, when we give cos for the general equation, we also will use cos for the modulating signal, so that easy for you to do the calculation. Okay, normally we give question either sine and sine or cos and cos. Doesn't matter, no problem. Previously we have seen cos, sine and sine. Now we want to see cos and cos, just a slightly different. Okay, so from here we can define the equation for phase modulation. From the general equation we can define the phase modulation equation. Just change the theta t to become kp vmt. So it becomes vc cos omega in bracket omega ct plus kp vm cos omega mt. Okay, so this is actually vc cos 2 pi f ct plus kp vm cos 2 pi fm, close big bracket. Okay, and for the frequency modulation equation equal to vc cos omega ct integral of kf vmt. Okay, so we need to change this one. We need to change theta t to become integral of theta prime t. Integral of theta prime t dt. Theta prime t is kf vmt. Okay, kf vmt is theta prime t, and we integral over over the time dt. Okay, so vc cos 2 omega ct or 2 pi f ct plus integral of kf vm cos omega mt. So vmt is cos, and then we can put outside kf vm, and then integral of cos we get positive sine. Okay, positive sine over omega m. So this is actually equal to this one, vc cos bracket 2 pi fct plus kf vm over 2 pi fm cos, sine 2 pi fm t, close big bracket. Okay, I just changed the omega m to 2 pi f. Okay, saya tukarkan omega kepada 2 pi f. Okay, so in the previous exam also we have asked the student to define the complete equation of fm and pm. Pernah ditanya dalam exam Okay, this is the frequency deviation to show the frequency deviation for the carrier. Okay, you see that for the fm and pm, the carrier frequency will change from carrier rest frequency to high frequency, which is fc plus delta f, and it will also change to the minimum frequency, which is fc minus delta f. So carrier frequency change in accordance to the amplitude variation of the input message. So you see that when the input message goes through the maximum peak, positive, fc will be at maximum. Okay, and when the signal moves through the maximum negative peak, carrier frequency would be at minimum frequency, and so on. Okay, so you see that the carrier frequency change in accordance with the amplitude variation of the input, and later you're going to see that when the frequency of the carrier change, we are indirectly change the phase of the carrier as well. Okay, so carrier and frequency and phase happens at the same time, but indirectly. Okay, you will see later, okay, about that. So both, when we change the frequency of the carrier, the phase of the carrier also will change indirectly. secara tak langsung. Okay, so delta F here is what we call as frequency deviation. Okay, so the range of carrier frequencies is from Fc minus delta F until Fc plus delta F, and the total range is 2 delta F. Delta F plus delta F, so 2 delta F. So this is what we call as carrier swing. Carrier swing. Okay, the total range of carrier frequency variation. Delta F is the frequency deviation. Okay, delta F is frequency deviation. So carrier swing is 2 times the frequency deviation. Okay, and this one I will explain. This is the last slide I will explain today. Okay, about the wave. Okay, so let's learn about the wave, because this also has been asked in the previous final exam. Okay, where you need to understand how does the wave looks like. Okay, so originally it's difficult for us to differentiate whether this is a FM or PM, because both of it looks alike. Okay, dia adalah hampir sama. Okay, so in order to differentiate FM and PM waveforms, we need a reference wave. Okay, we need to compare side by side with the carrier signal and also the modulating signal. Okay, so you see that here, this is the carrier, A is the carrier, and this is the modulating signal. So this is VCT, this is the VMT. Okay, and this C here is VFMT, and here is the VPMT. Okay, and you see that for VFMT and VPMT, C and D, the amplitude of the carrier is not changed. Only the frequency and phase is changed. Different from AM. In AM, the amplitude of the carrier change up and down. Now the frequency and phase change means that the right and left, the ripple of the wave is changing. Okay, in accordance with the amplitude variation of the VMT. Okay, so you see that originally, okay, let's look at picture C. Okay, graph C for the FM. Okay, initially the wave is at rest frequency. Rest frequency means FC, at center. Okay, and then what? So the input move from 0 until positive maximum. So what happened is that the output will produce maximum negative deviation, which means that the carrier frequency would be at the minimum frequency, which is Fc minus delta F. Okay, minimum at this point. Okay, and then the modulating signal move through the from positive to the x-axis, which is what we call as a zero crossing. Zero crossing means the wave will move either from positive to negative polarity or negative to positive polarity. Okay, so when the modulating signal cross the x-axis or zero crossing, it will be at rest frequency. Rest frequency is Fc. Okay, and then the modulating signal moved towards maximum negative peak. So what happened? The output will shows the maximum positive deviation. Means that the output will produce the maximum frequency, which is Fc plus delta F. So you see that the ripple of the waves is close one another. Okay. And then what? The modulating signal move from negative peak until x-axis or zero crossing. So the output gonna be at rest frequency Fc at this point, and so on. So you see that for frequency modulation, the peak changes happen when the modulating signal reach the peak amplitude. Okay, the critical changes happen when the modulating signal reach the peak amplitude, either positive peak or negative peak. Okay, and then what? Let's look at graph D for PM. So what happened for PM? So you see that initially at rest frequency, okay, so for PM, the critical changes happen at zero crossing, different from FM. For FM signal, critical changes happen when the modulating signal achieves the peak amplitude. While for PM phase modulation, critical changes happen during the zero crossing. Okay, so you see that here at this point, okay, at this point, this is the wave move from 0 until peak positive. So Fc would be at Fc plus delta F maximum. Okay, and when the wave, so maybe I need to erase the above part, so I erase this one so that, wait, okay, so when the wave achieve the maximum positive, what happened is that the output would be at rest frequency, which is at Fc at this point. Okay, and when the wave move from positive to negative, it will cross the zero axis, zero crossing. So what happened is that the output will shows the maximum negative variation. Negative variation means that Fc, F carrier will be at Fc minus delta F. Okay, so from positive towards negative, it will produce output with minimum frequency, the minimum frequency. And when the modulating signal reach the negative peak amplitude, what happened at the output is that it will be at rest frequency, which is at carrier frequency. Then it move again, modulating signal move again towards zero crossing. Okay, zero crossing. So what happened at the output is that the output is become maximum positive deviation. Okay, because this is from negative towards positive, so the output gonna be at highest frequency, which is Fc plus delta F at this point. So that's why you see the ripple of the wave is close one another. Okay, gelombang itu rapat-rapat. So it is the highest frequencies, and so on, dan seterusnya. Okay, so this is the so you see that as a conclusion, for the phase modulation, critical changes happen at zero crossing, while it becomes rest frequency when the modulating signal achieve the peak amplitude. Okay, critical change happens at zero crossing, and during the peak amplitude of the modulating signal, the output would be at rest frequency. Okay, so we have asked these questions previously. We have asked this question previously, where we give a wave. We give three waves. The carrier, the modulating signal, and either FM or PM. Okay, we give carrier, we give a modulating signal, and we give either one of these. Okay, and the student needs to know whether this is a FM or PM. Okay, and if the student already determined whether this is for example PM, for example, the next question asks about the characteristic. What happened when the it achieved the maximum? What happened if the modulating signal achieved the maximum positive? What happened if the modulating signal achieved the arrive at the zero crossing again? And then what happened? So students need to explain about that. Okay, pernah ditanya. So the question is more like a theoretical concept of understanding about the wave for FM and PM. Okay, so you see that in this subject, the question is more about theoretical concept understanding. Okay, the calculation is not difficult. Okay, calculation question is not difficult. Okay, because the most difficult I think is this one only, the integral. That's it. Okay, there's no other difficulty other than this. Okay, so if you think that this is easy, then very good. Okay, just a simple integral, sine and cosine. That's it. Okay, so that's all for today. If you have question, you can ask. Okay, about this. Kalau ada soalan boleh tanya. Kalau tak ada, if you don't have question, then we can end this session. And next week gonna be mid-sem break. Okay, mid-sem break and Hari Raya holiday, Idul Fitri holiday. So we're gonna have 1 week of holiday. Very good. So you will have 1 week holiday. Me maybe not 1 week. Okay. If I want a 1 week holiday, I need to take my annual leave for the extra holiday. Okay. So that's all for today, and you can open your QR code reader for the attendance. Okay, for the attendance. So I will open the attendance list. So I will open the QR code. So please open your QR code reader to scan the attendance. So here, okay. So today is 26. Okay. So if you have scanned your attendance, you can go outside. Okay. So happy holiday and selamat hari raya. Okay, to all of you.
Thank you, Doctor.
Okay, welcome. Selamat hari raya. Okay, selamat hari raya to all of you.
Doctor,
Yeah.
for me, before I cannot scanning.
Pardon? Can you scan the attendance?
Doctor, I cannot scan the attendance.
Yeah, doctor, for my phone, just the camera.
Okay, so what's your name?
My name is Usama, doctor.
Your name is Usama.
Doctor, I also cannot scan, doctor.
Okay, your name is Usama. Okay, done.
Can you help me?
Yeah, doctor, thank you, doctor.
Okay, who else?
Muhammad Amir Amri, Doctor.
Muhammad Amirul Amri. Okay, done.
Thank you, Doctor.
Okay,
Selamat Hari
welcome.
Raya.
Selamat Raya. Who
Okay,
else?
Doctor, thank you. Doctor, 25.
25. Iwanina. Okay, done.
Okay, Doctor. Selamat Raya, Doctor.
Okay, Selamat Raya.
Doctor, number 11.
Okay,
Doctor.
what's your name?
Mama Joki.
Muhammad Jokri Tali. Okay, done.
Doctor, number 8, Kumaran Naidu.
Kumaran. Okay, done.
Hello, Doctor.
Huh?
Doctor, I see in my attendance it is 83.3. 83.3. So what happened?
Pardon, could you repeat again?
I see my attendance. It is 83.3. So I don't know what happened.
What is 3.3? I don't understand.
It is my attendance.
Oh, I don't know about that.
May I send a picture?
Yeah, you can send picture. Where you want to send?
Your WhatsApp number. This is okay,
Okay.
doctor.
Have you sent to me or not?
I will send you now. Wait, doctor.
Okay, you can send later about that. So your name is, what's your name? Is it Sundus?
My name is Sundus,
Yeah. So
doctor.
now
I
your
attend
today
from
your
the
attendance. I already take your attendance for today.
yeah.
About the
But I
attendance
attend.
issue, you can contact me through WhatsApp later. Okay.
Okay, doctor.
Okay.
Thanks a lot, doctor.
Okay. Waalaikumsalam.
Bye, doctor.
Okay. Bye. Happy holiday to you. Eid Mubarak. Okay. Eid Mubarak to you.
Eid Mubarak too, doctor.
Okay. Mana Alif? Where's Alif? Where's Abdul Karim? Alif? Abdul Karim? So here, yeah, Abdul Karim is here. What happened? You are quiet. So I will take your attendance, Abdul Karim. Okay, done.